Hello everybody, my name is Carlos and this is my presentation for assignment 1 for our randomized algorithms and security science class for spring 2021. For this presentation, the professor has allowed us to choose two problems from the files he has shared, out of which I'm choosing the following. Problem 1 asks, we roll two standard six-sided dice. Assuming that the outcomes of the two rolls are independent, we want to calculate the probability of the following events. A, if the two dice show the same number. B, if the number on the first die is strictly larger than the other one. C, if the number on the first die is greater or equal to the other one. D, if the sum of the results of the phases is odd. And E, if the product of the numbers is a perfect square. For problem 2, we have the following. We assume that we have three events, X, Y, and Z, which are pairwise independent. We want to prove if these are necessarily mutually independent. So let's start. Problem 1 is a probability theory problem, and for us to be able to solve it, we need to be able to determine a probability space. That includes a sample space that will be used in other sections, an event collection F, which is the events related to each section, and a probability measure P, which is the probability of occurrence of each section and event. So since we want a common sample space, because we're using two six-sided die in each of the sections, we should be able to prepare a common sample space, which is the one that you see here. This denotes every possibility in a standard two six-sided die. Since we are drawing two, we are counting all the possibilities for each of the numbers. That is 6 times 6, 36 possible outcomes. So now we start with the sections. For section A, we get the following. We want to know if the two dice show the same number. Coming back to the sample space, we see that the only ones are this diagonal here, which is basically 1, 1, 2, 2, 3, 3, and so on. Since we get numbers from 1 through 6, we only get 6 possible outcomes. That makes our E6. So the probability, in order for us to be able to find it, we need to have the event length over the sample space, which in this case is 36. So we want 6 over 36, and simplifying, that is 1 over 6, which also equals to, in decimal, to 0.1667 or 16.67%. Now, the percentage part is not really required, but it's going to come in handy for a small demonstration that I'm going to show you later on. Section B asks us if we want to find the number, the combination so that the number on the first die is strictly larger. So since we want a number that is larger than the second one, we need to discard any that start with a 1, because in the best case scenario, we're only going to get a similar number, which is 1 and 1. And that does not satisfy the condition for the section, which is that the first die has to be really larger. So in that case, if we come back to our sample space, we're going to notice that the only ones that satisfy this are this staircase of sorts that goes below the numbers that are equal, and that gives us this collection. So from here we can see that we get a staircase again. One outcome for 2, 2 outcomes for 3, 3 outcomes for 4, and so on. So that gives us a total of 1 plus 2 plus 3 plus 4 plus 5, that's 15. And the probability would be, again, having the collection over the sample space, that is 15 over 36. Simplifying, this is 5 over 12, which is 0.41667 or 41.67%. Section C asks us to get the combination so that the number on the first is greater or equal. Now, this sort of hits a deja vu here, because we're noticing that we're asking first if the number is greater or if the number is equal. meaning that both of these cases satisfy the condition. But since section A asks us for when we get the same number, and section B asks us for when we get a number that is 3 larger than the second one, the event collection is a simple matter of simply stacking the first collection onto the first section's collection onto the second section's collection. So that gives us our E to amount to 6 from the first one and 15 from the second one at 21. So the probability for this event amounts to E over sample, that's 21 over 36, and simplifying that's 7 over 12, or 0.58333 or 58.33%. So section D asks us to get a combination where the sum is odd. To be able to understand how we get an odd number out of two numbers, we need to understand how additions of two numbers work. And there are three simple conditions. If both numbers are even, the sum is always going to be even. That's 2 plus 2 equals 4, 4 plus 4 equals 8, 6 plus 6 equals 12, and so on. If both numbers are odd, then we're always going to get an even. 1 plus 1, 2, 3 plus 3, 6, and so on. If one of the numbers is odd, as long as one of them is odd and the other is even, the solution is always going to be odd. 1 plus 2 equals 3, 2 plus 3 equals 5, 3 plus 4 equals 7, and you get the idea. So, although I didn't really display here, you can see that in the sample space, for each row, only three conditions satisfy: 1 and 2, 1 and 4, 1 and 6, 2 and 1, 2 and 3, 2 and 5, and so on. So we get that the E of the event collection will be 18. And conversely, if we want to find when the sum is even, it will be also 18 because it's the other numbers. But in this case, the probability will be the event over sample, 18 over 36, 1 over 2, 1 half, or 0.5 or 50% chance to get it. Section E. We want the product of the numbers that is of the faces, which will give us a perfect square. So a perfect square is basically any number that comes as the result of a number multiplied by itself. So 1 times 1, 2 times 2, 3 times 3. And it may appear simple because in this case I've only used similar numbers to get a perfect square. So in this case, we can naively assume that the solution would be the same as the first section, in which we want both faces to be the same. But it is possible to get a perfect square out of the product of different numbers. So for example, if we get 6 times 6, that is 36, we can get also 9 times 4 to get 36. 8 times 8 equals 64, which is also 16 times 4. 10 times 10 equals 100, which is also 25 times 4. Here we're only focusing on our regular dice faces, which go from 1 to 6. So we need to explore from those numbers. Also, to make our life easier, there is the commutative property of multiplication, which basically states that the order of factors bears no change in the product. So we only need to examine 1/2 of the sample space as divided by the diagonal of the same numbers. So in this case, we get 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 2, 5, 3, 4, 3, 5, 4, 5, 5, 6. The whole section, the whole triangle, if you will. And for here, we want to find the multiplications. 1 times 2 is 2, 1 times 3 is 3, 1 times 4 is 4, and so on. And from this, we find that the only one that satisfies the perfect square condition is 1 and 4. But the commutative property is not going to exclude the outcomes for the other half. So we must also count 4 and 1, which is 4 times 1 is 4, obviously. So to get the event collection for the perfect square, we get 1 and 4 and 2, plus anything from the event collection of the same number. That is 6. So 2 plus 6 equals 8. And finally, we get that the probability for the event is event collection over sample space, that's 8 over 36, simplifying, that's 2 over 9, or 0.222, or 22.22%. So here's my demonstration. I created a small program in CodePen, which allows us to create JavaScript-based programs for the front end and run them online. Because this homework doesn't necessarily imply using programming, I'm not going to go into details, but basically we go over a bunch of dice throws depending on the number obtained, inputted, and then we get results and stats based on these numbers. So seeing the stats here, I chose to use 10,000 because that's a reliable limit to be able to see an accurate statistic. So from the first one, we want to get when the dice are the same, and we get a 16.58%, which is similar to our 16.67% result. Then to get if the first die is greater, we get a 41.37%, very close to the 41.67% that we got. Then we get if the first die is greater or equal than the second, that's a 59.95% probability. And the result that we got on the PowerPoint was 58.33. To get if the die sum is odd, we get a 50.5%, very close to the probability that we got when it's 50%. And if the dice pro is a perfect square, we get a 22.39%, which is close to the 22.22% in the presentation. So we can conclude that our findings are accurate, and also that the math.random function in JavaScript is reliable to use. So on to problem 2. In order to be able to understand what we're being asked, we should be able to clarify some vocabulary, some definitions. Independence, what we understand for independence would be if we know that the certainty of one event occurring doesn't change the probability of the other. So in a formula, we can explain it how it happens when two events intersections are equivalent to the multiplication of their individual probabilities. And this is noted by P of x and y is equal to P of x times P of y. Pairwise independence is sort of an extension of this. Whenever a pair of events intersections, the probability of both occurring in an outcome is equivalent to the multiplication of their individual probabilities. Meaning that if we have three events, such as in this case, we're going to find the independence that bears true for P of x and y equals P of x times P of y, and P of y and c, and P of x and c. And mutual independence basically states that whenever the independence can be perceived across all intersections of events, meaning that we not only want the pairwise independence check, but also verifying that all the events included, in this case 3 events, P of x and y and c should be equal to P of x times P of y times P of c. So, based on the definition, pairwise independence only relies on 3 operations being true. Mutual independence relies on those 3 and another one. So from here we can conclude, just from looking at it, that any mutually independent events have to be pairwise independence, but not the other way around because of that extra step, because of assuring independence among all events. In order to be able to prove this, we have an example. Let's assume we have a bag of 4 balls and that we want to draw one at random, such as the one on screen. And we want to define the probabilities of getting odd, getting a perfect square, and getting less than 3, and ensure if these are pairwise independent, and thus if they are mutually independent. Now, given that our sample space is all of the balls, 1, 2, 3, and 4, and 4 total outcomes, the events could be defined as event A, as it says, getting odd, that's 1 and 3, so equal to 2. Event B, getting a perfect square, that's 1 and 4. also 2, and event C getting less than 3, that's 1 and 2, so also 2. So the probabilities would be P of A 1 over 2, P of B 1 over 2, and P of C 1 over 2. So for pairwise independence, we need to ascertain that P of A and B equals to P of A times P of B, and that P of B and C equals to P of B times P of C, and that P of A and C equals to P of A times P of C. So here we can see that A and B equals to 1, because that's the element that they have in common. 1 and 3 and 1 and 4 have 1 in common. So P of A and B would be 1 over 4, because that's 1 of all of the sample space. And we test that P of A and B equals to P of A times P of B. So 1 over 4 should be equal to 1 half times 1 half, which is 1 over 4. And this is true. And since the others also have the same probabilities and the same common elements, we can confirm then that these events are pairwise independent. But in the case that mutual independence, we want to check for the big one, and that is if the probability of A and B and C is equal to P of A times P of B times P of C. So first, in order to be able to find P of A and B and C, we need to be able to find that the event collection for A and B and C. In this case, is 1, because that's the only common element. So P of A and B and C would be 1 over 4. And finally, we get that P of A and B and C, which should be equal to P of A times P of B times P of C, is equal to 1 over 4 equal to 1 half times 1 half times 1 half. 1 over 4 equals to 1 half times 1 half times 1 half. This would be 1 over 4 equals to 1 over 8, but that's obviously not true. So because we cannot ascertain that the dependence of all events is equal to the multiplications of the probabilities, we can say that events A, B, and C are not mutually independent. And therefore, we're proving here that not all pairwise independent events are mutually independent. This concludes my presentation. Thank you for watching, and have a great day.